So now we have questions on the movie about delta H and bond energies. And the whole idea of this is that when you do a reaction, you break bonds in the reactants and you make bonds in the products. Breaking bonds requires pulling two things apart that are attracted to each other. That requires energy. That's endothermic. Making bonds is the opposite. So if breaking is endo, making must be exothermic. And you can say that delta H is the combination, the net effect of all that breaking and that making. So let's do 3 examples. First one, hydrogenation, double triple bonds, important industrial process, jolly good, who cares? Calculate delta H for the hydrogenation of acetylene to ethane. Well, if you haven't done the organic modules, then you don't know this, but that's all right. I give you the equation there. And I'll give you all these bond energies. So let's look at the structures of what's going on. We've got acetylene here, plus 2H2, going to ethane there. And I've drawn it as Lewis structures. I've drawn it with all of the bonds on display. If you're not sure about Lewis structures, well, there's a nice couple of modules of those already been released. Now what we do is we look at it in terms of bonds being broken and made. We break bonds, which is endothermic, in the reactants. So we've got to break a carbon-carbon triple bond, and the energy of that is 839. We have to break 2 HH bonds, and you've got to have 2 because remember all these are per mole, so we've got 2 moles, so we've got to break 2 moles worth. So that's 432 times 2. Now in this particular question, I'm not breaking that carbon-hydrogen bond because it's still there. I don't break it and make it again. I just leave it as it is. Same for this carbon-hydrogen bond. So I'm breaking bonds, the triple bond and 2 of these hydrogen-hydrogen bonds. And that gives me a total of 1703 would be kilojoules. Now then on the other side, I'm making some bonds, and making is exothermic. What bonds do I make? Well, I make that nice CH single bond, and the energy of that is 347. And then I also make 1, 2, 3, 4 CH bonds. Okay, already had those ones from before, so I'm not making those because I didn't break those. I'm making 4 CH bonds, and CH bond is 413, so 4 times 413, add all that up together and we get 1999. So delta H is the net of these. I need 1703 kilojoules, but I get back 1999 kilojoules. Delta H is the endothermic 1703 and the exothermic minus 1999. Delta H minus 296 kilojoules. Question 19, same idea, but I'm going to present it to you in a slightly different fashion. Okay, first of all, the reaction is N2, that's with the triple bond, and H2, that's with a single bond, to make N2H4, that's with a nitrogen-nitrogen bond and 4 nitrogen-hydrogen single bonds. And of course, one must not forget the stoichiometry. It's not 1 HH, it's 2 HHs. So now we're going to break bonds in the reactants. We're going to make bonds in the products. Breaking the bonds, we have the NN triple bonds, 941. We have 2 of the HH bonds, each of which is 436. And making, I've got the NH, 389, and I've got 4 of those, 1, 2, 3, 4. I'm also making an NN single bond that is 159. Add them up. I'm breaking 1813 kilojoules worth. I'm making 1715 kilojoules worth. Put it all together, 1813 for the endothermic breaking, minus 1715 because the making is exothermic, and I get delta H equals 98. Finally, a little question that is exactly the same idea but phrased ever so slightly differently. Given the reactions below, what's the NN double bond energy in kilojoules per mole? Well, the first one is NH3. There's the Lewis structure of NH3 going to an N and 3 H atoms. How do I do that? I've obviously broken 3 NH bonds. The next reaction, This funny little N2H2 there's got an NN double bond, and then of course each N has an NH bond. Breaking it into its atoms again, well, to do that I've broken 2 NH bonds, and I've also broken an N double bond N. Now I'm told the delta H values. Well, the delta H for this first one, where I'm breaking 3 bond energies of NH3, is 1173. Thus the bond energy of NH3 is 1173 divided by 3, or 391. Down here, I'm not just breaking 2 NH, I'm breaking an N double bond N, and those add up to the 1200. Well, I already know what the NH is, it's 391. I don't know what the N double bond N is, but I can figure it out now. N double bond N is the 1200 overall, minus 2 of the NHs, because this 1200 corresponds to breaking an NH and an NH and their NN double bond. So the NN double bond, 418 kilojoules per mole. Fun little questions. Conceptually, I think easy. 2 mistakes people make. The first is they flip the signs. We're breaking bonds in the reactants, that's positive. We're making bonds in the products, that's negative. And a lot of times people will remember the last thing, the Hess's law, delta H of the reaction, is the heats of formation of the products minus the heats of formation of the reactants. And they'll put that the same. They'll do products minus reactants. Well, it's not products minus reactants. It's breaking bonds in the reactants, which is positive, making bonds in the products, which is negative. And then the other ways that people mess up on this are they will just forget the coefficients, they will maybe not draw the structure out, they'll maybe not break all the bonds or make all the bonds. Conceptually easy, fun to do, very easy to slip up.